Okay, welcome back, everybody. We're on lecture 7 now. It's almost October. Time is flying by. Okay. So, last time we talked about two main things. I guess maybe three main topics. So, I think I actually forgot to put the first one here on this review from last time. But we started off looking at how salinity varies, and also temperature and density, but mostly salinity, how it varies with depth. There were a few key features that we saw that apply basically to anything. So it applies to temperature and salinity and density in terms of how they vary from the surface to the bottom. And these couple of representative curves, they show these various features. So this is now salinity, and so just as a reminder, so there's two curves. One is for low latitudes and one is for high latitudes. And the way that you can remember that is that the low latitudes are where you have a lot of warm atmosphere, lots of insolation, and so that's going to lead to evaporation. So at the low latitudes, you're going to have high surface salinity. So we have the one with the higher surface salinity, that's the low latitudes. And at the high latitudes, you have lots of runoff and stuff, so you have a low value of surface salinity. But then the very interesting thing was the structure in the vertical, and we identified sort of three main features. So the first feature is that up at the top, there's this layer called the surface mix layer, where if you look at the curves, they're vertical lines. So what that means is that as you go down, the salinity value is not changing. And so what that means physically is that some processes have been sort of homogenizing that upper layer, sort of stirring it and mixing it up so that everything is totally uniform. We talked about the reason for that, and it has to do with two effects, and both have to do with turbulence. So in the wintertime, if you have a very cold atmosphere over the top of the ocean, that tends to cause convection. So you cool the surface layer, that layer gets more dense and it sinks down and causes convection. And the other mechanism is wind, so just mechanical forces acting on the surface because of the winds. They also stir up the upper layer, and so we have lots of turbulence and convection driven by winds and thermal in this upper layer, and that stirs it up, and so you get this surface mix layer where the properties are pretty homogeneous. And so this is showing salinity, but if you also look at temperature or density, they're also pretty uniform. And then in the deep ocean, and usually when we say deep ocean, we mean below about 1,000 meters. Once you get to the deep part, the salinity is pretty uniform. So we have a pretty uniform value of about 35 parts per thousand, and that's also true of temperature. So if you look at the temperature of the deep ocean, it's fairly close to the freezing point of water, and it's fairly uniform no matter where you look. And then in between, that connects the surface to the deep, there's this layer called the halocline, where the salinity value changes rapidly from the base of the mixed layer at about 50 or 100 meters down to about 1,000 meters. These numbers, they vary a little bit from over space and time, but roughly those are good numbers. And the halocline is where the salt changes rapidly. Thermocline is very important also. That's where the temperature changes rapidly. And then when we want to talk about density, which comes from the combination of the salinity and the temperature, we call that the pycnocline. And so after that, we moved on to this idea of how the atmosphere and the ocean are coupled. And we said that really it's sort of a combined system where each part of the atmosphere and the ocean influences the other. And the system overall is driven by differential heating. So the sun heats the Earth more at the equator than at the poles. We're actually going to talk about that in more detail today. And that sets up wind circulations in the atmosphere. And we all sort of know that when winds blow over the surface, that drives waves and it drives circulation. But the ocean also influences the winds, and one example we talked about was El Nino. So we're going to cover El Nino in more detail later. But the key thing is it's a big surface warming. So these large patches, huge like continental scale patches of the ocean, they warm up by several degrees, and that warms up the base of the atmosphere, and that changes the winds. So it's a two-way street. The sun sort of drives the atmosphere drives the ocean, but then the ocean also recouples and influences the atmospheric flow. And then the last topic we touched on was trying to understand just why is it that we do have this differential heating. So what are the various mechanisms involved that cause the equatorial regions to get more sunlight and solar energy than the polar regions? And there were a few different reasons. One of them had to do with this area effect. So if you think of the sun coming in as like a flashlight beam, that beam of photons is concentrated over a relatively small area at the equator, but you can see those photons are smeared out as you go to the poles. And so if you look at any small patch of ground, at the poles it's getting less photons per, say, meter squared than at the equator. The thickness of the atmospheric layer also has an effect, and this very interesting effect we talked about was the albedo. So the albedo is how much light the surface reflects away, with the high numbers like 0.9 is the albedo of ice, so you reflect away 90%, whereas something like 0.1 means you absorb 90%, only reflect away 10. And albedo, the main thing it depends on is what the surface is made of, so whether it's ice or ocean or trees or whatever, but it also depends on the angle. So we talked about how at high latitudes, the sun sort of comes in at this slant angle. So if we had the surface of the ocean, if the photons are coming in at a slant angle like that, they tend to be reflected off pretty efficiently, whereas if they're coming in sort of at a 90-degree angle, then they're absorbed very efficiently. And so all these factors come together to give us this distribution, which is how the watts per meter squared, the annual average insolation, varies over space. And we see that we sort of got a big red band in the middle, and then down to the more green colors, meaning weaker insolation at the poles. Okay, so today we're going to move on to talking a little bit about what's the structure of the atmosphere. The atmosphere is separated into various layers, much like the ocean is. We talked about surface mixed layer and then the deep, so the atmosphere has layers also. And then also what kinds of motions we're going to start talking about. What are the sorts of motions and the physics that goes on in the atmospheric flow, meaning the winds. And we're going to touch on things that are thermally driven, so convection, and then also other key forces that are involved. And in particular, we're going to talk about pressure forces and the Coriolis force. Okay, so just to set the stage, it's worth it to just spend a minute to talk about the composition of the atmosphere. So I think we all have seen this before, but this is a pie chart that's showing of just air that we live in the lower layer of the atmosphere. What's the composition? And it's mostly nitrogen. So it's about 80% N2, so we get the two nitrogen molecules, or two nitrogen atoms bound together in a molecule. About 20% oxygen. It's a diatomic molecule with two oxygen atoms. And then the rest of it, so that's almost all of the gas is oxygen, nitrogen. But then there's small amounts of other gases. Argon, CO2 is very significant as a greenhouse gas. And then there are trace amounts of other gases as well, including, say, for example, methane, ozone, nitrous oxide, some pollutants, things like that are present in small fractions. It's important to remember, though, that sometimes, even if a gas is only present in a small amount, it can still have a big effect. So, for example, methane doesn't show up on this plot, but if you study climate change, we might talk about it. We might talk about methane a little bit toward the end of the course, maybe not. But if you take another course on climate change, we'll talk about methane, because methane, even though it's a very small concentration, it has a very important greenhouse effect because of its sort of the way it absorbs energy, the way it absorbs light. So this is the overall composition of the atmosphere, and that's fairly uniform. The atmosphere is also divided up into layers. So this might be a little bit new unless you've taken a course in meteorology. But there are basically three key zones in the atmosphere, and we think of them as vertical layers. So you think the altitude in kilometers we should use on the left-hand side here going up, surface down here, and sort of the top of the atmosphere, or like almost going up into sort of outer space or inner space at the top. So we live in this bottom layer, which is called the troposphere. And so just to give some context, so the troposphere, we usually think of it as being about 10 kilometers thick. It can be maybe 15, a little bit higher. It depends on actually latitude, depends on exactly where you are. But the highest mountains we have on Earth, they still only exist within the troposphere. So no building, no mountain gets up into the higher levels, but they get somewhat close. So the highest mountains are maybe 8 or 9 kilometers, and the troposphere is about 10. And so all of our weather that we experience, all of our human activities, with one exception, go on in the troposphere. And then at the top of the troposphere, there's a boundary that's called the tropopause. And then above the tropopause, there's the stratosphere. The stratosphere is a very thick layer, goes from about 15 kilometers all the way up to about 50 kilometers. And commercial air travel actually travels, if you're in sort of cruising altitude, your airplane will be somewhere near the tropopause. It could be the upper troposphere or lower stratosphere. You don't get into the middle stratosphere, it's always the low part, but these planes can kind of just touch the bottom of the stratosphere. And the stratosphere is called that, the strato part. It comes from stratification or stratified. So we talked about when we looked at the Earth structure, we said that the densest materials, like the metals, they're the heaviest, the most dense. So they sink towards the center of the Earth, and then the lighter things like the silicates and that kind of thing are on the outside. So we have the heavy stuff on the bottom and the light stuff on top. So the stratosphere is the same way. It's very strongly, stably stratified. Actually, so I forgot to, this is a very important detail I forgot to mention here. So the red curve that goes up through these layers is actually the temperature. So something we all know very well is that in the troposphere, the temperature decreases as we go up. So as you raise your altitude, the temperature goes down, and that's why there's snowy peaks on the top of mountains, because it's very cold there, so instead of getting rain, you tend to get snow. And so as you go up through the troposphere, the temperature is decreasing, and then at the tropopause, actually the temperature trend, it reverses, and it starts to warm up through the stratosphere. Very, very interesting. So the upper part of the stratosphere is actually much warmer than the bottom part of the stratosphere. And what that means is that you have warm, buoyant air sitting on top of cold, denser air, so it's very stable. So that warm air doesn't want to sink down, it wants to stay at the top. The reason for that is very interesting, and it has to do with ozone. So the stratosphere is where much of the ozone in the atmosphere resides. And ozone is actually very effective at absorbing solar radiation. So you probably have heard of the ozone hole, in certain places where the ozone the ozone layer maybe has been reduced over time, it was actually a worse problem in the past because of these things called CFCs that we then banned. There was this thing called the Montreal Protocol. But we used to do a lot of damage with certain chemicals to the ozone layer. Now we have banned some of those chemicals and the problem has been improved. But if you don't have ozone, what happens is a lot of UV light gets through from the sun and gets down to the surface, and that causes bad sunburns, and it causes skin cancer. And so ozone sort of protects us from that. But the fact that it protects us means that it absorbs those photons. So if you have lots of ozone in the stratosphere, it absorbs these high energy photons coming in from the sun, and when it absorbs that energy, it warms up. And so the upper layer of the stratosphere is quite warm because it's absorbing those photons, and that's why it's so stably stratified. And then above that, we get into the upper atmosphere, usually for meteorology and climate, we don't care about the upper atmosphere too much. The air is very thin up there, so as you go to higher and higher altitudes, the pressure goes down, the density goes down, and so the amount of mass that's in the upper atmosphere is actually very small compared to the troposphere. And so usually we don't think about it that much, but for some things it's very important, and one of those things is the aurora borealis, or the northern lights, which is this very cool magnetic phenomenon, and that's happening in the upper atmosphere. So I just want to show a really interesting meteorological phenomenon that happens in the stratosphere that I just really like, and I've sort of done some research on this before. It's called the quasi-biennial oscillation. So biennial in this context means every 2 years, and the quasi means almost. So it's an oscillation that happens over 2-year cycles, but it's not exactly 2 years, it's just close to 2 years. And this is this figure, which is from data. I think so. This is atmospheric observations at some particular locations, the time. So it's a time series. So time runs from 1953 up through the 50s, and then starts again in the 60s. So time goes from left to right, and then top to bottom. So we go from 1953 here all the way up to 2013 or so at the bottom. And what the colors are showing is the direction and the strength of the wind. So when you have, and the y-axis here is altitude. So this picture is showing from about the bottom of the stratosphere at about 18 or 20 kilometers altitude up to sort of the middle stratosphere at about 35 kilometers altitude. What the colors are showing is the strength and direction of the wind. And so this is all in meters per second. So the darkest red colors are 40 meters per second wind blowing towards the east. And then the darkest blue colors are 40 meters per second blowing towards the west. And the amazing thing that should jump out is that it goes red, blue in this alternating pattern. So what that means is, if we look at a particular level, let's say 25 kilometers here, and we just pan across time, so this is going forward in time, from 1953 to 1954, the winds are blowing to the east because it's red, and they're blowing fairly strongly at the beginning, about 40 meters per second. And then around the transition from 53 to 54, the winds reverse direction and now blow from east to west. So we've got western winds heading west at about 40 meters per second. Then in 55, it switches back to east. 56, it switches back to west. And so we're going towards the east, west, through time. And it repeats on about a 2-year cycle. Not exactly 2 years. And so this is really amazing. So if you were sitting, it's almost like the climate, it's like in the stratosphere. So we have this jet stream that blows from west to east in the troposphere. So if you fly, for example, from Newfoundland to Toronto, it takes longer than flying from Toronto to Newfoundland. Probably most people have encountered this at some point. That's because you're flying against the wind when you fly to Toronto, and you're flying with the wind when you come back. So if we lived in the stratosphere, that situation would change every year. 1 year it'd be faster to fly west, the next year it'd be faster to fly east, which I find pretty amazing. And when this observation was made, it really shocked people that worked in meteorology, and they came up with all kinds of ideas for how to explain it. And actually, the person who ultimately figured it out was my PhD advisor's advisor. Figured this out with a team of a few other people. And the physics is a bit. The physics of how to understand this is a little bit beyond the second year course, so you could maybe take this in a graduate course or a fourth year course. But essentially what happens is this is a wave phenomenon. So we're going to talk later in this course about various types of waves, especially ocean surface waves. And it turns out waves can carry with them, they can carry energy and they can carry momentum. And this whole phenomenon in the stratosphere is driven by waves in the atmosphere that are sort of very much like surface waves on the ocean that propagate from the troposphere up into the stratosphere, and they carry with them lots of momentum. And then that momentum drives the flow to go positive and quite fast, and then you have a negative momentum burst, and it causes it to go negative and quite fast. And so it's all wave transport of momentum that causes these oscillations. And again, that's not supposed to be totally clear, but just the general idea that waves are involved, and it's sort of a problem in theoretical physics. And this was sort of a big achievement in meteorology, was understanding this. Okay, but that's sort of just a general interest kind of topic. Okay, so what we're moving towards now is, so that was the stratosphere, but most of the things that we care about for the ocean are the troposphere, because the troposphere is the lowest layer, so that's the only layer that's in contact with the ocean. And so we want to now try to start building an understanding of what kinds of climatological circulation, so what are the average flows like the jet stream, also how do weather systems work, and that kind of thing. And as we said, it's really driven by thermal effects because the sun is heating the equator more. And so we're going to talk about convection in the atmosphere. So when we say convection, we mostly mean rising and sinking of air that's largely due to temperature differences. And so we all know warm air rises, and that's because the air is less dense, and then the cold air sinks, that's because it's more dense. And so if you had a situation like this in a room where you had a heater on one side and a cold window on the other side, the air near that cold window is going to get cold, get denser, and sink down. The air near the warm side is going to get warmer, more buoyant, and rise up. And then what tends to happen is that they form this circulation cell, or this circulation pattern, where there's heat flowing from the radiator across to the window, and you get this circulation cell. It turns out that temperature is the main effect that causes convection, but there are also some interesting other effects that have to do with moisture. They're less important, but they're interesting. And so I'll just ask you a question. So if we have air that's moist, so this picture is just considering dry air, so zero humidity. But if we have moist air, so that the air has some water vapor content, all other things being equal, temperature, pressure, so for example, if you're at the Earth's surface, is moist air more dense or less dense than dry air? Anyone have an idea? Have you seen this before? Or?
More dense.
And why do you think that?
Because now you have the water vapor in it.
Mm-hmm.
Making it denser.
So that's true. So certainly, if what you did was you took a fixed volume of air and you just stuffed more water vapor into it, then it would have to get more dense, right? But it turns out that when you put, but at the Earth's surface, for example, you don't have air in like fixed chambers. The air is exposed to the rest of the air, and so it's really at fixed pressure. And so when you add water molecules, say, vapor, to a sample of air, that air changes volume because those water molecules, they take up space. And so it turns out, this is not obvious at all, I did not know this until I was in graduate school, that moist air is actually less dense. It's very counterintuitive. Everybody thinks it's more dense, but it's actually less dense. And the reason is because if you think about a water molecule is H2O, and that water molecule actually weighs less than oxygen and nitrogen molecules. Because these hydrogens, their molecular weight is pretty small, whereas O2 and N2 have higher molecular weights. And if you think about the ideal gas law, the ideal gas law says that the volume of a sample is proportional to the amount of moles of molecules that are in that sample. And the amount of moles is equal to the total mass of the sample divided by the molecular weight. So when the molecular weight goes down, that means the amount of moles goes up, which means your volume goes up, which means your density goes down. So it's a little bit of a complicated argument, but essentially our lower molar mass of water means you have more moles, means you have a higher volume and a lower density for the same mass. So if you think of 1 kilogram of air, if that 1 kilogram is made out of water molecules partially, then you actually have more molecules total in that box, and so it's going to have lower density. This is sort of an interesting fact. It can actually lead to important physical effects in the layer just above the ocean where the air is very moist. But generally, when we think about convection, I just kind of wanted to point this out as an interesting physical fact, but generally when we think about convection, temperature is the main effect. Okay. So we have this idea that warm air rises and cold air sinks. But part of the goal of this course is to sort of apply physical concepts to understanding the climate system. And so we want to ask, beyond the basic qualitative idea that warm air is going to rise, we want to apply physics ideas now to say, how fast is it going to rise? So at what rate? And the normal technique for doing this in physics, you want to understand the forces on any object, like in this case, say a bag of air or a cube of air. We use the technique of drawing a free body diagram to look at the forces on that air. So here I just have a little schematic. So we have, let's think about the idea that we're over by the radiator, and so we have a cube of air, that's going to be the warm air, and then that's surrounded by air that's relatively cold. And so the warm air has a density rho warm, so we use rho for density, so W means warm here, and then the cold air, relatively cool, has a density rho cool. So the cool air, the rho C, is going to be higher than rho W. And so what's our free body diagram look like? Well, so here's our parcel of air in the middle. And so there's going to be two forces that are acting on this parcel. So we have the force of gravity that pulls it down, that always acts on anything. And then we have the force of buoyancy, and that comes from Archimedes' principle that's pushing it up. If the air was the same density as the surrounding air, so if you just have air that's just sitting there, or water that's just sitting there, and everything is the same temperature, everything is the same density, then when you're in a static situation, these two forces cancel exactly. The buoyant force and the force of gravity just balance, and everything is happy to just sit there. But when the densities are different, that's no longer true. And we can work out which force is going to win. So the usual thing we'll do is we'll write down Newton's second law as F equals ma. In this case, we're applying F equals ma to this warmer parcel. So the mass of that parcel is going to be equal to the density of the warm air multiplied by the volume. So that's your mass in your F equals ma formula. And now the force is equal to the difference of the buoyant force pointing up and the gravitational force pointing down. So now what are these forces? So the force of gravity, that's equal to the mass times the gravity. So we have the mass of our parcel times gravity, and then in the next layer we have here the mass is the density times the volume. So our mass is the warm density multiplied by the volume, and our downward gravitational force is that mass, rho times v, multiplied by gravity. So this is the downward force that's pulling our parcel down. And then the upward force is the buoyant force, and that comes from Archimedes' principle. So to calculate that, we need to know what's the mass of air that our parcel displaces. So we have this parcel of warm air, and it's pushing away all of this cold air on the outside. So the mass that it's displacing, the mass of cold air that otherwise would be in this location and has been pushed away, is now equal to, the mass is equal to the density of the cold air, rho c, multiplied by that volume, and then to get the buoyant force, we multiply that mass by gravity. So we get the cold density multiplied by the volume multiplied by g. Okay. So we have our two forces, force of buoyancy, force of gravity, and it's the difference between them that's going to decide whether there's an overall upward force or an overall downward force. And we can see by factoring out the factor of g is in both terms and the factor of v is in both terms. And so we get this difference in forces, the net force that's acting on the parcel, so the difference between the upward buoyant force and the downward gravitational force, ends up being, after some factoring, volume times gravity times the difference in densities. So the cold density minus the warm density. And because this cold density is going to be higher than the warm density, so the cold air is denser than the warm air, this number is going to be positive, rho c minus rho w, and so we're going to have a positive force that's going to lead to the parcel rising. So that's how we know, that's the physical reason why warm air rises. So warm air rises really just because of Archimedes' principle, because it's more dense, or sorry, the warm air is less dense than the surrounding air, and so it's going to have a positive net force with buoyancy outcompeting gravity. So then we can actually solve for the acceleration. So if we go back to Newton's second law, we now have our mass is density times volume. We have our net force is this difference in densities times v times g. And we can set this up as Newton's second law. So we have, this is the mass here, rho times v, times the acceleration, and that equals the net force. And so we can find the acceleration just by dividing by rho and v, and we get this formula. So if you were going to have to use this formula, for example, to calculate an acceleration on an exam, for example, I would give you the formula like this. But so the acceleration ends up being equal to gravity times this density difference, and again, the cold air is denser than the warm air, so this is a positive number, divided by the density of the warm air. And so we can actually use physical principles to calculate the exact rate at which a parcel of air is going to rise or fall. And I think on the second assignment, or maybe the third assignment, you'll get to sort of play with this formula and estimate for ocean water how fast or how slow is it going to rise or sink when it's embedded in water of a different temperature or salinity. Okay, so temperature, and to a much less extent moisture, affect density, and then density creates buoyant forces, and those result in accelerations. And so now we're going to try to apply those general principles to the flow in the atmosphere. Yes?
Just wondering, is the acceleration for the movement of the warm air or the cool air?
It's for the warm air.
Okay.
Yeah. So the acceleration that we're calculating is associated with whatever is the object in the free body diagram in this case. So we're applying F equals ma to this parcel of warm air. And so this acceleration that we calculated is for this warm air parcel. Now, it's of course true that if that warm air parcel starts to move, then it's going to push away the air around it, and it will cause some circulation of not just this warm air, but also the air around it. And so if you really want to know exactly how is the whole system going to move, not just the parcel we're interested in, but everything, you have to go a step beyond free body diagrams and thinking about this as a box of air, and you have to solve what are called the fluid mechanics equations, where you don't just track one parcel of air, but you track them all simultaneously and how they interact. And that's what's done in, so this is the 2300 Introduction to Oceanography course, but in the 3300 Intermediate course, we do that analysis. And so you can track the whole flow and how temperature differences, for example, drive everything. Yep. But it is true that it will have an effect on the surroundings. But when we draw a free body diagram, the acceleration is the acceleration of the object whose forces are being considered. Okay, so how would this apply in the atmosphere? So we're going to start with the sort of a simple example that's a little bit inaccurate, but it shows the general idea. And then we're going to move on to how it really works in the Earth's troposphere. We have this example of the radiator on one side and the cold window on the other side, and that sets up this convection cell. And you might think that the Earth's atmosphere is going to work something like that, because we also have these temperature differences at the surface that are driven by the sun. So the sun heats the equator more, it heats the poles less, and so we might have some kind of convection cell that's set up, driven by that temperature difference. And so something that people like to do, I mentioned fluid mechanics and solving all the equations for the full flow. It turns out mathematically that can be challenging to do. And you had to use computer software to do it. But one way to avoid the mathematical complications is just to do it with an experiment. So something that people like to do sometimes is sort of study fluid flows using simple experimental setups. And so this is an example. So this is a journal article from about 20 years ago, published in the Journal of Fluid Mechanics, which is one of the main fluid physics journals. And they tried to do this exact idea. So they built an apparatus where they said, we're going to model the equator and the poles by just taking a box of fluid, and then they have a heating mat on one side, and that's going to represent the tropics or the equator. So you're going to heat the bottom part of this half of the box, and on this side, we've got a heat exchanger with a cold bath. So some cold water over here, and you're sort of running the cold water underneath here. And so this side is being cooled, and this side is being heated. And then I think what happens is the side of the box is made of clear glass or something, so you can look in and you can see how the flow is moving. And they put some dye in the water, and then based on how the dye moves, you can characterize the circulation. Okay, so here's what came out of their experiment. So they turned the heating element and the cooling on. And so remember, so this side here represents the equator, and this side here represents the poles. So what you see is they put some dye in along the bottom, and the first thing that happens is you get this upwelling plume, they call it, on the left-hand side. So you get the water here is rising up along the left boundary, and that's because of buoyant forces. So it's warmed up. It's less dense than its surroundings. It experiences that buoyant force that competes gravity, and it starts to rise. And then when it continues to rise, it flows out along the top of the box, and you create this convection cell that flows across the entire experimental chamber. And they did a complementary computer experiment, and what they found was that the equilibrium, so after you let it run for a long time, so keep the heating stable, eventually it will develop some steady circulation, just like you might think our climate circulation is roughly steady. Right? We have the same jet stream roughly every year, etc. And so this is what the circulation looks like. You have the equatorial heated region over here and the cold region over here. And so along that leftern boundary where the heating is the strongest, you have a rising plume. It flows all along the top of the container. We have sinking motion, and the sinking motion descent, that's happening where the cooling is the strongest at the right-hand side, and then the convection cell is completed along the bottom. And so we have some circulating cell, and then you can also see that there's some interesting physics that happens. We have sort of a recirculation eddy here, and some interesting feature here. And so to understand these detailed features, that's what you need to use sort of detailed fluid mechanics physics to understand that. But the basic idea is when you have warming at the surface, like what happens at the equator, you're going to have rising fluid, and then wherever you have your coldest part, you tend to have sinking fluid. And those two things tend to be connected in these convection cells. And what that's ultimately doing is you're taking warm water from here, transporting it all the way over here, where it's going to get cooled when it touches this cooling mat. So it's called a thermally direct circulation. It moves the heat from where it's hot to where it's cold. And that's just like we said was necessary in the climate, because otherwise, because of the differential heating, our equator would just warm and warm and warm, and the poles would cool and cool and cool. Okay, so what are the actual forces? So we talked about buoyant forces, but it turns out that the buoyant forces actually have their basis in pressure forces. And so I want to talk about the pressure forces just briefly. So the fundamental force that drives fluid flow is generally pressure forces. And actually you can analyze buoyancy forces, Archimedes' principle. You can actually derive Archimedes' principle by looking at pressure forces. And so the idea is if we have some box of fluids, we often call this a parcel, so some parcel of fluid, maybe it's water, maybe it's air, then that parcel is squeezed on all of its sides by pressure forces, which is essentially all of the little particles are kind of trying to expand and they're pushing on each other. And so this little bag of air or water, it's getting forces on all sides. We have a pressure force on the right-hand side, a pressure force on the top, on the left, and on the bottom. And the pressures, they act on the sides of this box. So this is the basic idea of pressure. So we have a bag and it's getting squeezed. But it turns out it's not always squeezed the same in all directions. And the reason for that is that pressure is what we call a field in physics, which means that it's a number. So the pressure is a number that characterizes the local water, the local air. But it depends on where you are and what time it is. So the pressure varies in space and it also varies in time. So you imagine if you have some kind of, and we know this, for example, from weather reports. So if you look at a weather forecast, it'll often say there's like low and high pressure systems. There's these L's and H's on the weather map and they move around and stuff. And they move around in space and they move around in time. So this pressure would depend on your X and Y, maybe your latitude and longitude, also your altitude, and also like whether it's today or tomorrow, what time it is. So if the pressure is not uniform, so if it varies from place to place, what that might mean is that if you look at a bag of air in your flow somewhere, there could be a high pressure on one side and a lower pressure on the other side. That's something that might happen. In that case, the pressure force, in this case, we have a big arrow on the right-hand side, so the pressure force is pushing harder on the right-hand side of the parcel, and it's also pushing in on the left-hand side, but not as hard. And so what that means is that the pressure on the right-hand side, where the pressure is high, is going to win and try to push this parcel overall to the left. And so there's going to be a net force, we call this the pressure force or the pressure gradient force, that's going to overall push this parcel to the left. So it's getting squeezed, but because the squeezing from the two sides is not equal, the whole parcel of air is going to try to get pushed downstream one direction. So and usually how it goes is it goes from the high pressure to the low pressure. And that's the way the pressure forces work. Okay, so now we can look at how does this work in the Earth's atmosphere. And so this is a little bit of a complicated figure, but I'll sort of walk you through it. And you might want to go back and look at it in the notes because it's sort of an ugly, hard to look at figure. But what this is showing is if you look closely, no, I gotta look closely and figure this out. So where is, okay, so that's Newfoundland right there. So this is North America. So underneath, so there's all these circulating lines, but underneath this, they're showing the continents. So this is North America, that's Greenland there, there's Newfoundland, South America. And over top of that, they're superimposing the pressure contours. And so what these are is these circles here are lines along which the atmospheric surface pressure, which you measure with a barometer, is constant. And the numbers here are showing the pressure values in what are called hectopascals. And this is just a standard unit of pressure. And the key observation is that if you look at these numbers, so here, for example, we've got 1,012, 1,010, 1,010. This is the equatorial region. We've got 1,010, 1,014, 1,012. These are the equatorial numbers. And then if we look at the mid-latitudes, we've got 1,018, 1,016, 1,018. So off the equator, we're getting slightly higher numbers. So we have more like 1,010 in the equatorial region, and then we move into the mid-latitudes or the tropics, we get higher values. And so what this is saying is that we have a lower surface pressure right near the equator. It obviously varies in a complicated pattern because there's all these bullseyes and circles and stuff. But in general terms, you have lower pressure values here, and then higher pressure values just a little bit to the north and a little bit to the south. And so if you think about what this means in terms of the packets of air, it means that the pressure forces that are, the forces that are pushing you down here, the high pressure squeezing you here and squeezing you here, are going to be a bit larger than the pressure forces you experience from the equator. And so a slightly cleaner way of plotting this is this plot. So this is now showing, so now latitude from South Pole on the left-hand side to North Pole on the right-hand side with the equator in the middle. This is showing the surface pressure averaged along a latitude circle. So right at the equator, we have this dip, and so this means you have a lower surface pressure at the equator, and then near the two tropics, 30 north and 30 south, you have these locally high pressure peaks. And so that means you're going to get air, strong forces pushing you in and pushing you in here, getting squeezed hard, and then the forces that resist that squeezing are weaker at the equator, and so it's kind of trying to drive a flow in towards the equatorial region right along the equator. And so what are the impacts of that? Well, we might imagine that if here's your, let's say, so we have, here's the minus 30 south, equator, we have 30 north. So you have high pressure here, and a high pressure here, and a low pressure here. So the pressure forces, they point from high pressure to low pressure. So that means we're going to have a force that's pointing in this way, and a force that's pointing in that way. So you might expect, and this is exactly where it's warm, it's the warmest. And so you might expect that air is going to get pushed in towards the central equatorial region. So we're going to have airflow coming in, and then it has nowhere to go but up. And so you might expect air is going to get converged in towards the equator, and then it's going to maybe rise as the two sides hit each other. And so there's a very sort of simple conceptual model we can look at of what would happen if the Earth was not rotating. So we're going to shortly talk about the effects of the Earth's rotation, which are extremely, extremely important. But to get a basic idea of how do these pressure forces and these temperature differences drive a flow, we can look at this sort of example of a non-rotating model. So we have sun's rays are coming in from this side. We're heating the equator more than the poles. And then because of these pressure forces, we have air that's moving in from the tropics to the poles. It meets another wind that's coming in from the southern hemisphere. And then that warm air rises at the equator. And then just like our simple experimental model, you create a convective circulation. And so you have rising air where you have the warmest part of the surface, and it goes all the way to the poles, and then sinks down where you have the coldest part of the circulation. And so if the Earth was not rotating, which it is, so this is not an accurate model, it's just a conceptual model, we would have a equator to pole convection cell with rising at the equator, sinking at the pole, and a planetary scale circulation that moves heat from where it's warm to where it's cold. And actually, there are other planets in the solar system that work like this. So you may or may not have seen this before, but the different planets in the solar system, they rotate at different rates. So the Earth obviously rotates once per day. That's how we define the day. But Venus rotates very, very slowly. I don't remember the numbers, but it's much, much slower. Maybe it's 100 times slower. So for sort of practical purposes, Venus is basically not rotating. I think we don't have the best observations of Venus's atmosphere, but from what I have seen, the atmospheric circulation looks kind of like this. So you actually do have a planetary scale, equator to pole, convection cell going on there, because it really works like this model. Pressure forces and thermal forces drive this thermally direct heat transport. Okay. It turns out that basic physics, that you have rising air where it's warm and sinking air where it's cold, that still applies on Earth. But because of the Earth's rotation, that equator to pole cell gets messed up, and things behave quite differently. So to talk about the Coriolis force, we just need to briefly mention this idea of inertial frames versus non-inertial frames. So this is a little bit of sort of fancy physics terminology, but what an inertial frame is basically it means a frame of reference or a coordinate system where you're either stationary or you're moving at a constant speed. And so, for example, if you're just standing still, or if you're in a car that moves at a constant speed, what that means is that Newton's laws are going to sort of look normal. So, for example, if you're in a, let's say you're in a truck, and that truck is moving down the road, and you're in this truck, and you're taking a ball and you're throwing the ball up and down. So if the truck is going at a constant speed, that ball's motion will appear normal to you. It will go up and down, and the fact that the truck is moving is not going to affect anything. And that's called the inertial frame. And a non-inertial frame is anything else. So anytime you're moving at a non-constant speed, so you're accelerating, or you're turning, or you're doing anything other than moving in a straight line, that's called a non-inertial frame. And can anyone say, so if you were in this truck and you were tossing the ball up and down, what would happen if the truck started accelerating? So they step on the gas, they start going faster and faster. What's going to happen? Yeah?
The ball would not accelerate the same way, so it's kind of like, I don't know how to describe it. Like, towards the back of the truck, I guess.
It would go towards the back of the truck, right. So if the truck is heading this way and it's accelerating, and I'm throwing the ball's going to come back and hit me, right? And so the ball in the truck is going to seem like there's another force that pushes it back into you. And it's not really a force, it's just that you're in this box and the box is accelerating. And so we know this, we feel the same thing, for example. So when you're in a car, and let's say you're on a car on the highway and you're going on the on-ramp, when that car makes a left turn, you feel like you're kind of thrown against the door a little bit, right? You're sort of pushed against your seatbelt is pushed against the door. Also, when you're in an elevator, when the elevator starts to accelerate, you feel like gravity gets stronger, right? You feel like you're pushed into the floor, and when it starts to stop, you feel like you're a little bit lighter than you normally are. And if you've ever jumped in an elevator, you can jump kind of high. So those things are called they're called apparent forces or non-inertial forces, and those show up whenever the frame you're in, or your sort of frame of reference, or the observer, is accelerating. And that turns out very, very important to the climate system. And so the key question is the Earth's surface, where we make all of our observations, is that an inertial frame or is it a non-inertial frame? Does anyone have any idea which one would apply to the Earth's surface?
It would be non-inertial.
And that's correct. And so why is that?
Because it's also moving around the sun. The sun is also moving, so.
Yeah. So it's moving around the sun. That's part of it. The main part actually is that it's spinning on its own axis. It just turns out both of those things actually contribute, but the main thing is that it spins on its own axis. So if we think about the Earth's surface, if you're on this surface and an observer was viewing you from space, because of the rotation of the Earth, later on you would be over here, and later on you're over here. So your velocity vector is into the page here, and then it's this, and then it's out of the page, and then it's to the right. So you're sort of moving around in this circle. And we all probably remember at least the terminology from first year physics is that when you're moving in a circle, you're experiencing an acceleration called the centripetal acceleration. It's mv squared over r or whatever. And so because you have an acceleration, that centripetal acceleration, that means that you are not moving at a constant velocity. You are accelerating, and so that means that you're in an inertial frame. I think the last thing I'll just do is I have a video here. I'm going to go back and talk about this again next class. But just in the last couple minutes, I just want to show this video which illustrates the basic physics of how the Coriolis force works. And it's just 2 minutes, so that's just about the right amount of time. And so I'm just going to play this.
With a simple game of catch, I think I found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion. Here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate to the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it, all right.
Yeah.
What's going to happen, dude? Oh, it's going to veer off to the left. So the ball is going to swim off to the left. Yep. And you might catch it. Possibly. Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's
confident.
not catching it. He's not
Really?
catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right? Right, in your own time, throw the ball.
I got this.
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So somehow you threw the ball, it left your hands, And then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curve right in.
Right, so we all agree here the ball curved in midair.
Yeah.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected.
Okay, so we'll actually show that video again next time, and we'll talk about this idea. But the connection to the Earth's atmosphere is that we're on this spinning Earth, and it kind of works like this merry-go-round. So objects like they curve in space. Yes.
The video we just watched, like was the direction the merry-go-round going to affect.
Yes, it completely determines it. So if you spun the merry-go-round the other way, it would curve the other direction. Yeah. And so on Earth, actually it turns out that the northern hemisphere and the southern hemisphere are kind of, in some sense, spinning opposite ways. And so actually the Coriolis force works opposite in the northern hemisphere versus southern hemisphere. Yeah, so we're going to talk about that next time. Great. Okay, see everybody on Friday. And just as a reminder, the assignment is due 11:59 this evening.